Now consider again the multiple linear regression problem where we have a matrix X where the rank R of the matrix is strictly less than the dimension. So it is not a full rank. And in this case, we've seen that the estimate itself of the parameters is not unique. So in other words, there's a whole set of these B's, boldface B's should be where the expected value of Y is XB, but they're not unique. So it's not just a single estimate. The X prime X matrix does not have an inverse. But we've also seen that the estimable functions, they have unique estimates. And so we would like to consider how do we set up constraints to make these things unique. And in the simplest examples, we just look at the problem and decide on some constraint or other. So in a one-way layout, for example, we can say we're going to make the sum of the alphas 0, or we're going to set alpha 1 0, or we're going to set alpha, the last alpha, alpha I in this case, equal to 0. And these different approaches are used by different pieces of software and for different purposes. However, there is a generic way of doing this, which is to say, look, we'll just specify a matrix, a general matrix, and we'll estimate we're going to try to estimate beta so that we do get the same value of the predictor. And the side constraint is that H beta is equal to 0. Now, if we choose such a matrix, H, in such a way that we get the rank of the combined matrix equal to P, then this matrix, combined matrix, is invertible. So we can solve the combined problem of trying to minimize Y minus X beta and the simultaneously H beta equal to 0. And what happens here then is that these betas become estimable. Now there's a detailed proof of this in Shefei's book, but we can take a quick look at this and notice that if we write G for this combined matrix, then we can look at G beta tilde instead of just X beta. And G beta tilde now is X beta and a 0. So when we multiply things together, all sorts of nice things happen. For example, G prime G, if we write this out, G prime is X prime H, so put up adjacent to each other, and then we have an X and an H. And when we lay this on its side to pair it with this, what we end up is X prime X plus H prime H, or H transpose H, if you like. And now this guy, remember G has rank P, so G prime G is of full rank and is invertible. So we can take the inverse here and solve uniquely for a beta tilde. Now this is of the form C times beta, right? And we find that if we define beta tilde hat to be the corresponding inverse times X prime Y, then the expected value of beta tilde hat is equal to X prime X plus H prime H inverse X prime Y the x beta, expected value of y is still x beta. And now remember that g prime g beta is equal to exactly this thing here at the end, and g prime g is also equal to this number. So this is equal to g prime g beta g prime g beta tilde. This stuff here is g prime g inverse. So this whole thing is equal to beta tilde. So we have an unbiased estimate. We have an estimate of the form a times y, which is unbiased for beta tilde, which means that beta hat tilde is indeed an estimator of the appropriate form ay. So beta tilde itself is an estimable function. And this is what we wanted to show. To continue with our earlier example, the very simplest example of this is to look at the one-way layout again. And so here we have yij equal to mu plus alpha I plus epsilon ij. And let's just take the very simplest case where we have each j going from 1 up to j and I from 1 up to I. So a fixed number of observations per treatment group. And here our X matrix, or if we start off by arranging our Y's within groups, so Y1J, Y21 to Y2J, and then this keeps on going to YI1, YIJ. This then we write as an X times the vector of all parameters, and the parameters are mu alpha 1, alpha 2 to alpha I, plus an epsilon vector, which we won't write out. The mu appears in every single one of these. This is the multiplier for mu, and then it keeps on going to the last one. The alpha 1 only appears in the first one, and then you get zeros from then on. And then the alpha 2 only appears in the second one. And then we get all zeros to the last one. And this keeps on going, zeros in the end, except for the very last block where we get ones. So in this case, if you transpose this, put the ones on the sides, you'll find that x prime x is equal to, you multiply this column by itself, and you get simply n, where n is I times j. And then for the next one down, you get j, and you get j along the entire diagonal. So that's your x prime x matrix. At the top, you will have this particular one paired with each. So you'll have j here in each of these locations, j all the way down to j. And you should note here that this matrix does not have an inverse, because if you add up the rows below the first one, then you will get exactly n, j throughout, first n and then j's throughout, which is the same as the first row, so these are not linearly independent. Now, if you choose, for example, to put your H matrix as 0 and then 1, 1, and so forth, you're basically saying the sum of the alpha I has to be 0, and then H prime H is a matrix of the same dimensions as this one, and it's left up to user to figure out exactly what this looks like and to demonstrate that actually x prime x plus h prime h does indeed have an inverse.